It's a fun proof. Yeah, I'm going to do it. All right, sorry. It's just pain or otherwise. I just can't not do it. So this is actually the result of the product rule for derivatives. So if I were to take, I'll just do it off on the side here. If I were to take the derivative of u times v, all right, so the derivative of u times v with respect to x. It's important. It's got to be with respect to something, right? You'd have the first function multiplied by the derivative of the second function plus the second function times the derivative of the first function. All right, so you have this big mess. And it's really not much of a mess because you've seen it before. That's calculus. I'm blowing up here. But somehow this has to get to this, right? So we start thinking about, well, how can we orchestrate this? Well, one thing we can do is actually multiply through with a dx. All right, so we'd be looking at duv would be equal to uv prime plus vu prime dx. All right. So then, again, with an eye on what we're trying to end up with, so we have u dv minus, or equals uv minus the integral of v du. We're looking at these main ingredients. These would have to be equivalent to one another in some fashion. All right. So we start looking at the u prime and the v prime. So v prime is the same as dv dx. U prime is the same as du dx. If you multiply through with a dx, we now have duv equal to u dv plus v du. Again, like I said, keeping an eye on what we're looking for here. It's kind of cheating here, but it really just boils down to a matter of preference at this point, because if we could have a u dv alone or a v du alone, right? It's just the way the formula is set up, this integration by parts formula, it's set up to have the u dv alone. So that's what we're going to do. All right. So I'm going to isolate that by subtracting v du from both sides. So we're looking at u dv is equal to duv minus v du. All right, so that's a relationship between variables. It's wonderful. I mean, it's structurally the same as what the rule is telling us it is. The only issue is it doesn't have any integrals in it. All right, the left-hand side has the integral of u dv. So I'm going to integrate one side of the equation. But if I integrate one side, I have to integrate both sides. So the integral of u dv is going to be equal to, if I look at this a piece at a time, the antiderivative of a derivative, those are inverse relationships, they cancel out. It's going to leave me with just a uv. Minus the integral of v du. All right, so this is a formula that really is just the extension of the product rule for derivatives. All right, so it's a product rule for derivatives just manipulated in a slightly different way. All right, it's if you were to take the product rule and just solve for something else and then take the antiderivative at some point, you would get this rule. All right, what this allows us to do is take the product of two functions and break them up in a different way. All right. So what does that look like? Well, practically speaking, it's not that bad, but as we learn new techniques, the idea keeps coming into play over and over again. How do I know it's going to be this kind of problem? All right, and aside from like a rundown of what's going to be on the test, you got to diagnose in some capacity, right? If you look at each of these examples, with the example, forget about 3, right? Because that one, I mean, it's got bounds, so you just throw it in the calculator anyway. But I like this problem because it shows you how you can use integration by parts for a concept that doesn't seem like it would work. But in each case, you're looking at the product of 2 distinct factors, all right? 2 different types of functions being multiplied together as part of an integrand. That's your key indicator that what you're dealing with is integration by parts. U substitution won't work, right? Because if it would, you'd use that. All right, so can I define a u here that would allow me to cancel out the other factor? If I let u equal e to the x, that's not canceling out an x. If I let u equal x, it's not canceling out e to the x. So, no bueno. All right, same idea over here. So that tells us that integration by parts is at play. Because every other technique that we're learning in this unit involves fractions. I mean, you haven't seen the remaining topic, which is partial fraction decomposition. We'll get to that tomorrow. Very straightforward, at least the way I teach it. It involves fractions based on the title. It's called partial fractions. All right. The trig substitutions, fractions. All right. The stuff that we did yesterday, that's all trig. Right? It doesn't look anything. These have e's and logs, and some of them have trig in it, but they don't look like the kind of problems that we were working on yesterday. So the look of a problem is a key indicator of what you're supposed to do. All right. So the tips are to try letting dv. We're going to define 2 things. We're going to define u and dv. All right. So think of this as like an extension of u substitution. We're defining u, and we're also defining another variable dv. We're going to try letting dv be the most complicated of the integrand that fits a basic integration rule, and let u be a portion of the derivative of the integral whose derivative is a function simpler than u. All right. What I mean by all that is I'm going to define 2 things, u and dv. In this process, we're going to be taking the derivative of whatever we call u. We're going to be taking the antiderivative of whatever we call dv. All right, so you think about that for a second. We're going to take the derivative of the thing that we're calling u. We're going to take the antiderivative of the thing that we're calling dv. What that means is, whatever I'm calling u, I better be able to find its derivative. Whatever I call dv, I better be able to find its antiderivative. Otherwise, I'm making the wrong selection. All right. An extra added component to that is when I take the derivative of whatever I'm calling u, I want it to lead to a simpler function. All right. So let me don't write this down, but let me give you the wrong u. If I take the derivative of this, will it make it simpler? Like if I were to take the derivative of e to the x, will I get a simpler function? No, because I'm getting the same exact function e to the x. Right? It will not be simpler than it was originally. All right. If I define u as x, will I get a simpler function? Yes. All right. So that's a key ingredient, but the most important thing is, all right, well, now I'm saying, well, the e to the x dx has to be my dv. All right, well, if that's the case, you have to ask yourself, can I find the antiderivative of e to the x? If the answer is no, then that might be a you problem. Like, you can't find the antiderivative of e to the x, but that's not really what the question is. The question really is, can anyone find the antiderivative? Is it antidifferentiable? If the answer is no, then you chose the wrong thing, right? But we know the antiderivative of e to the x is what? E to the x. So v would be e to the x, and du would be just 1 or dx. All right, we don't put the plus c here, even though we're taking an antiderivative, because this is not my final answer. If I were to put it here, it would still be fine. It's just I'd have to consolidate my plus c's later on in the problem. That's not going to be worth the energy. All right, so I have all my components. I have a u, I have a du, I have a v, I have a dv, so I'm good to go because my rule says uv minus the integral of v du is equal to the integral of u dv. All right, so x e to the x dx is equal to my u, which is now x, my v, which we just determined is e to the x, minus the integral of v, which is e to the x, du, which is dx. X e to the x minus, then I just need the antiderivative of this, which is e to the x, plus c, and that's it. Now, if I had gone the wrong way, it's possible that you could end up with something that you could work with when you get to this step, but most likely, if you choose the wrong u, once you get to this step, you come to an integral and you say, all right, well, that didn't help. So back to the drawing board. So you erase everything you just did and you start it over again. All right? It's annoying, but it's not the end of the world. All right? Because just like u substitution, you have a limited number of possible choices to define your u and dv. All right? So you try something that doesn't work, try something else. All right? You tried everything and it didn't work. Well, try something again. Or maybe you're using the wrong strategy. Right? Maybe it's trig substitution when you're trying to do partial fractions or something. All right. But these kind of problems tend to stand out. The more experience you get, the more you'll see. In the interest of time, I'll put a star on number 2. We'll skip number 3 for now. Don't even bother with it. At some point, we'll pick it up. I'm not going to ask you to do that on the test. It's a fun question, but it's not something I want to get into right now. If you're interested, I'll just tell you, if you're interested in trying number 3, the u is the arc sine of x, and dv is equal to dx. All right, so if you want to give it a go on your own, you can. The answer key's online, so you can look at the solution. Because intellectual curiosity sometimes haunts us. And, we can't stop ourselves. All right, but number 4, a little trig action going on here. Trig can be a little iffy. I mean, that's probably not the most intelligent thing I've ever said. It could apply in every number of possible circumstances. It's like, you think back to how we're defining u and dv. So u should be something that I could differentiate. Well, I could differentiate a trig expression pretty easily, as long as I know the rules. I could also anti-differentiate them, especially sines and cosines. right? But the idea that you want to have in mind is, will the derivative yield an expression that's simpler than what you started with? All right, so I'll do what I did before. I'll put the wrong u. I'm going to write the sine of x. The derivative of that would be equal to the cosine of x. Is cosine of x simpler than sine of x? No. No, because I asked the question, or no, because of a mathematical reason? Mathematical reason. Cosine is the complement of sine. It's the sine function. It's the same thing. It's just shifted over. All right, it's the same thing. All right. So you didn't get simpler. You stayed the same. All right. If I let u equal x squared, I will get simpler because du would be equal to 2x dx. So I'll let dv equal everything else. So sine x dx. All right, so I'll add a little layer to this. Ideally, now this is not a rule. It's not a hard, fast rule. du needs to get simpler, but dv, when you integrate, like, it can get more complicated. Like, you may have to do a reverse power rule, like power 2 becomes power 3. So, like, that's okay, but ideally it would not get more complicated. Like, the perfect storm is your derivative gets simpler while your antiderivative does not get more complicated. When I take the antiderivative of sine, I get negative cosine. That's no more complicated than the sine function is. All right. If I were to graph the two, they look very similar to one another. All right. One is no more complicated than the other. Now, if I were to looking at a secant becoming secant x tangent x, yeah, that just got more complicated for a derivative. So I'd want to stay away from that. But then you would think, like, okay, if I put the secant in as an antiderivative, now it's the natural log of secant x plus tangent x. Now it's like, wait a minute, I need the lesser of the two evils. Which is less painful, the derivative of secant or the antiderivative of secant? Go with the lesser of the two evils. Here, I think it's pretty obvious. All right, so u dv as an integral is equal to uv minus the integral of v du. So x squared sine x dx is equal to uv. So put these two guys together. Negative x squared cosine x minus the integral of v du. Now, so in that case, I'm putting, I'm going to go blue here, these two guys together. Make it a plus. And we're going to have a 2x cosine x dx. Now, this is a moment where perseverance needs to happen. Because you look at this and say, okay, well, screw that up. Because I can't take the antiderivative of 2x cosine x dx. So clearly this should be sine x and that should be x squared. What the hell is this guy talking about? With this whole making it easier, keeping it from being too complicated. Perseverance. You get to this step in the process, hey, you know what? Maybe you got to do integration by parts the second time. All right? So, and fun fact, that's exactly what we're going to do. I need to evaluate this because looking at the structure, it's still the product of two distinct functions, 2x and cosine of x. Just like this is the product of two distinct functions, x squared and sine of x. All right? So, do it again. And I'll show you in a second how it'll become a little bit more obvious under these circumstances how you would know to do it again. All right, so I'm going to let u equal 2x and dv equal cosine x dx. differentiate du equals 2 dx, anti-differentiate v equals sine of x. All right, this is the key here. Looking at the progression of my du's. See how it went from x squared to 2x down to a 2? Consistently getting simpler and simpler. In my integral, in my rule, there is always v du. It was, in this step here, the du part that kept me from being able to integrate this. If it were just cosine x dx, I wouldn't have had a problem. But that 2x is what caused the issue. If that x wasn't there, I wouldn't have had a problem. The next level is going to remove the x. All right, so by making your u's simpler and simpler as you go, you're progressing towards a solution. All right, also something to keep in mind, I can't combine these integrals because they're not the same. But if they had the same trig function in them, maybe I could. Like for example, if this were, if I got an integral here that said x squared sine of x, I could take that integral and add it to this one, actually subtract it in this case, and then simplify it out. That's a different story for a different problem, but sometimes you can combine integrals, so be on the lookout for things like that. That's why I write the entire equation. All right, so what I'm looking for here is 2x cosine x dx, cosine x dx is equal to uv minus the integral of v du. So 2x sine of x minus the integral of 2 sine x dx. Which is anti-differentiable. 2x sine of x. Antiderivative of sine x is negative cosine, offsetting with the negative that's already there. So plus 2 cosine x plus c. However, this here is just this part. If I want my complete final answer, I have to include that negative x squared cosine x. So, final answer, x squared sine x dx is equal to negative x squared cosine x plus 2x sine x plus 2 cosine x plus c.